Welcome to section 4.2. We're going to talk about is linear and quadratic functions. So here it'll cover linear functions, how they're graphed, quadratic functions, and how their graph looks like. Okay, so these are familiar ones because we've already talked about linear equations in two variables. That's basically linear functions. And then we talked about quadratic equations though, so this is something different, but it should be familiar in some ways. Okay, so let's start with talking about linear functions. It says here that a linear function of one variable x is a function that can be written in the form. This is very familiar. It's like y is equal to mx plus b is what you've seen in the previous sections. But that's the same thing because f of x refers to y. So here it's just f of x equal to ax plus b, where a is non-zero, right? And b is, it could be zero. We could have it zero, but a, you don't want it to be zero for a first degree equation. Why is it first degree? Because the power of x is 1. It's understood that there's a 1 there when you don't see it. Okay? Because we don't say x to the first power is just x. We just let it be x. Okay? So this is just, the usual y equals mx plus b that you've seen before. So what is the graph of the function f? It's x, and it's the set of ordered pairs x and y. Remember, y is whatever happens when you plug in the x into the function f of x. Okay, so x has to be in the domain of f. Now, graphs of linear functions are non-vertical, straight lines. So it could be horizontal, it could be oblique. In other words, it's slanted either you could have lines that are, say, sloping upward, or lines that slope downward, or horizontal lines. These are all linear functions, but you can't have a vertical. Why is that the case? Because when you have a vertical, it's not a function. Because remember, when you have a vertical, it fails the vertical line test. So suppose this is my function, and you say, oh, it can't be a function because once I use the vertical line test, it coincides with the line itself. The vertical line test fails. So the domain of all linear functions is the set of real numbers. Why? Well, because all you do is you take y equal to ax plus b, and there's no restriction. I can plug in any x to this function and I'll get a y. Say y is equal to 2x plus 3. So is there any restriction as far as what my x could be plugged in here? No. So that means the domain would be all real numbers. Remember, when you talk about the domain of a function, you ask yourself, is there anything that I cannot plug in? So if there's not, then you say it's all real numbers. Let's take, for example, the graph of, how do we graph the function f of x equal to minus 3x plus 5. And remember, this is just the same as your slope-intercept form. Okay, so you can just write this as, to make it more familiar, y is equal to minus 3x plus 5. And we can generate 2 points and we can determine the line, or you can plug in as many x's as you like. Like in this case, we could plug in -1. So once we plug in -1, how do we know how did y became 8? Well, if x is equal to -1, that means y is equal to -3 times -1 plus 5. That'll give us what? It'll give us 8, because negative times negative is positive 3, plus 5 is 8, and so on and so forth. Now, if x is 0, that's understood to be the y-intercept. Look, if x is 0, this whole thing is 0. So f of 0, you see that's f of 0, it's y. F of 0 is 5. If x is 1, Well, what happens here? Let's try that. Okay, so if x is 1, y is equal to minus 3 times 1 plus 5. And what does that give us? Negative 3 plus 5 is equal to 2. And so on and so forth. So if x is equal to 2, as you can see, when you plug in 2 in here, what will you get? Negative 6 plus 5, you'll get negative 1. And this is how the graph looks like. It should be a line, just like that. Okay? Now, why didn't we use the slope and the y-intercept of the line to draw the graph? Why not? We could, but here it just tells us that we can graph any value of x for that matter. And you see how you could have used the slope starting from the y-intercept, because the slope is negative 3. So you go 1, 2, 3 down for every step forward. 1, 2, 3 down for every step forward, and so on and so forth. Okay? All right, let's keep going. Now, what about these kinds of functions? Are these linear? Well, let's write it in a more familiar way, because remember y, or let's write it as y is equal to negative 4 times 3 minus x. Or if you want to write it in a slope point form, that becomes, distribute that over, you're going to get negative 12 plus 4x. So another way of writing is 4x minus 12. Okay, now how do we graph that? Well, the thing about this is if we use the slope intercept and you get the y-intercept to be negative 12, remember that in Hawks you can only plot from minus 10 to 10, both x and y. So we probably won't want to use the intercept. Instead, we just plug in any x and y values. So suppose x, we get the y, or remember your y is f of x. So say I can plug in, we can try using, say, 1. If we plug in 1, then that becomes 4 times 1 minus 12, we get negative 8. Okay? Then another number we could try is, say, if x is 4, what do you think y is? So 4 times 4 is 16 minus 12, you get 4. So now you can just use two ordered pairs. So all we have to do is just plot. So we plot for letter A, we plot 1, negative 8. So you see you don't have to use the slope, or rather you don't have to use the intercept to plot the function, because as we said, if x is 0, y is negative 12. It's way down below the range of values on when we graph it in Hawks. So this now is 4 and 4. So how does that look like? Let's try that. You start from, here is negative 8, and there's 4 minus 4, and then 8 right here. So if we plug in x equal to 1, what's y? Y is negative 8. 1, 2, 3, 4. And if we plug in 4, y is 4. So you see how we've generated those two ordered pairs? And once we have an ordered pair, two ordered pairs, it can determine a line. There you have it. And the graph verifies that, see, the domain is all real numbers, because we cannot confine this graph into a box on both sides. And the domain is all real numbers as well, because you cannot put a lid on the graph of this, because the line will keep going to plus infinity and it will all go down to negative infinity. So the domain is all real numbers and the range is all real numbers. So like I said, you can just plot the thing about this is that from here I'll show you another way of graphing this. Okay, because what we did here is we rewrote it into a slope-intercept form. Okay, we don't have to do that. I'll show you why. Okay, from here, what we can do is just generate a few ordered pairs. So another way of graphing it. All we need is just we just need two ordered pairs to graph this. And remember, we got to find those ordered pairs that are contained within minus 10 and 10 of x's and minus 10 and 10 of y's. So because of the way this is written, I can just plug in x, and you know your y is your f of x. We can plug in 3. Now why did I choose 3? Because it's convenient. If I plug in 3 here, it's just the way this linear function was written out. If I plug in 3 here, then y would be 0, or f of 3 is 0. Okay, another one could be, say, if x is, excuse me, and you see I could have used any other number. Let's say if x is 5, what is y? Well, if x is 5, that's 3 minus 5 is negative 2, and then negative 2 times negative 4 would be positive 8. And you still get the same kind of function. So let's see how we can plot that. Go ahead and try it. You've got 3 zeros right here, and then 5, 8. So let's say this is 3, and let's say that's 5. And then say this is 4 and 8. So these are the 2 points, and that could generate already. Okay, there's your line. Now let's try letter B. How about we try letter B? What do you think would be good points to plug in for letter B? Or what would be x's we could plug in for letter B? So for letter B, again, we don't have to write it as in the form y is equal to, you know, mx plus b. We can leave it the way it is, but we just have to figure out what would be ideal values to plug in so that we can get a reasonable or an easy value for y. Well, let's see. Remember, all we need would just be two ordered pairs to determine the lines. So two ordered pairs. So let's try. Okay, so we're in letter B. Let's try x and our g of x. As you notice, I interchange g of x or y. They mean the same thing, okay? So suppose, look, if I try 0 for the x, I'm going to get a negative 14 over 4, which is what, 7 over 2? Negative 7 over 2, that's fine, but, you know, we can pick out something that's easier to plug in. Notice that if I plug in x equal to 2 here, okay, what is g of 2? G of 2 is equal to minus 2 minus 14, whole thing divided by 4. And see how I chose 2 because, 2, it'll be minus 16 over 4, and that's equal to negative 4. So we have generated one ordered pair. Okay, another one that we could use is, say, something that would maybe add up to, how about we want to try 6. Now again, why did I choose 6? So let's try 6. Again, why did I choose 6? Because g of 6 would become minus 6 minus 14 over 4 will give us negative 20 over 4, which is negative 5. So these are just convenient numbers. So let's see. How is that going to look like? So say this is 2, 4, 6. So you have x is equal to 2, 4, and 6 right there. And then let's see, suppose this is 1, 2, 3, 4, 5. So here is minus 4. and here is -5. So let's plot those. So we said that's -5. So the ordered pair would be 2, -4, and then 6, -5. As you can see that the slope is really -1/4 right here. You see that? That's -1/4 x. So it matches what we anticipated. That's how the graph is going to look like. All right. So again, when you want to graph a linear function, sometimes it's just out of convenience. What would be to pick out the x that you want to plug in? All you need is just a set of 2 ordered pairs, and you're good.